Hi and welcome to this applied maths video. Today we're talking all things matrices. So let's start by asking, well, what is a matrix? So a matrix is a grid of numbers with rows and columns. And in applied maths, we're going to work exclusively with what we think of as square matrices. So square matrices have the same number of rows as columns, hence the name square. And what matrices do is they help us to store, organize, and then to manipulate information. And here's an example of a 2 by 2 matrix. That's because it's got 2 columns and 2 rows. And here is a 3 by 3 matrix. Again, 3 columns and 3 rows. Be very clear, the word matrix is singular, while the word matrices is plural. So what are matrices used for? So matrices are used to model systems and interactions, especially where things are connected. So when we're working in the networks and graphs section, which is all about connections, matrices become very important to us. So here are some examples of some real world uses. So for social networks, so who follows who? Maps and roads, so where can you travel between? Computer graphics, we can see it in Markov chains, which looks at predicting outcomes in games and decision theory, epidemiology, so how diseases spread from groups to groups, and board games and puzzles, so anything with like a grid-based movement we think of as having a matrix involved. So I'm going to jump straight into matrix multiplication. So when we do matrix multiplication, there is a lot more that we could do beyond the applied maths course. Again, I'm going to focus just on square matrices. So first, you multiply a row of the first matrix by a column of the second. And the order here is really, really important. It is the row of the first by the column in the second. So multiplication for us will always be possible, but it is really, really important that the rows in the first matrix match the column in the second matrix in general for multiplication to be able to work. So here's how it works. Imagine we have two matrices. I've just put in letters here. A, B, C, D in the first one and E, F, G, H in the second one. Both are 2 by 2 square matrices. If we want to multiply them together, what we do is we take row 1 of the first matrix and we multiply it by column 1 in the second matrix. What that does is it gives us the result to put into row 1, column 1 in the answer or the resultant matrix. So this is calculated as A by E plus B by G. So we're taking the first piece of row 1, multiplying it by the first piece of column 1, plus multiplying the second piece in row 1 by the second piece in column 1. And that will get us our answer. And then for the second place, we have row 1, column 2, which goes into that placeholder in our answer vector. So really focus on the position you're filling in, and that will really help you to understand, well, what are we multiplying? So when I fill in this piece here, which is row 1, column 2, I'm working with row 1 in the first vector, column 2 in the second vector. Be very, very clear that the row always comes first, and that's going to be a common thread throughout our vectors. So when we multiply these together, we get A by F plus B by H. And then we move down to the next row, which gives me row 2 in the first matrix by column 1. And that fills in as C by E plus D by G. And finally, we get row 2, column 2, which is C by F plus D by H. Now, if you're somebody who's not crazy about working with letters, let's work through a number example. So example 1, let's look at some basic 2 by 2 matrix multiplication. So here is our matrix A and B, and it says given the matrices A and B below, find AB, which means A multiplied by B. Just like in normal algebra, we would say two letters stuck together, there is implicit multiplication there. So we're going to multiply 1, 2, 3, 4 by 0, 1, 2, 3. So Let's work this. We start first with our first row and we multiply it by column 1. Remember, it's the first piece in each, so we get 1 by 0 plus 2 by 2. So row 1, column 1 is 1 by 0 plus 2 by 2. I'm going to come back and do the answers in a bit. I'm just going to focus on our actual multiplication first. Then we move to row 1, column 2. That's 1 by 1 plus 2 by 3. Then we move to row 2, column 1, and that is 3 by 0 plus 4 by 2. And then row 2, column 2 is going to be 3 by 1 and 4 by 3. And working each of those out, 1 by 0 is 0 plus 2 by 2 is 4. That just gives us an answer of 4. 1 by 1 is 1 plus 2 by 3 is 6. That gives us an answer of 7. 3 by 0 is 0, plus 4 by 2 is 8, and 0 plus 8 is just 8, and 3 by 1 is 3, plus 4 by 3 is 12, gives us an answer of 15. So our final answer for AB is 4, 7, 8, 15. So one thing to note is that matrix multiplication is not commutative. So first of all, well, what do we mean by commutative? So it's a word you probably hear a lot, but it's really important to understand what it means. In normal multiplication, we have this idea of commutative, which is that the order doesn't matter. So 2 by 3 is the same as 3 by 2. Really handy when we're working with adding and multiplying. But we do know that subtraction and division are not commutative if you change the order. So 5 take away 2 is not the same as 2 take away 5. So not all operations are commutative. But for us with numbers and algebra, they are commutative. But when we get into matrix multiplication, that's not true. So matrix multiplication is not commutative. And really think about this, because when we flip them, what's going to happen is the rows and columns end up switching. So we take the row from the first matrix by the column from the second, but then if we flip which one's first and which one's second, then we're flipping which one we take the row from and which one we take the column from. So we're not getting the same answer. So AB is not the same as BA when we're working with matrices. So let's dive a little bit deeper into that with example 2. Given the matrices A, B below, prove that AB is not equal to BA. So here's A and B. We've already worked with them in example 1, and actually we've already worked out AB. So we have part of the work done for us. So what we're going to work with now is we're going to work out the second part and figure BA. So I'm going to take matrix B and multiply it by matrix A. So we're going to use the same process. We're going to look at row 1 by column 1, and that's going to give us 0 by 1 plus 1 by 3. And then we look at row 1, column 2, and that's going to give us 0 by 2 plus 1 by 4. Then we work with row 2, column 1, and that's going to give us 2 by 1 plus 3 by 3. And finally, we have row 2 by column 2, which gives us 2 by 2 plus 3 by 4. And if we work through each of those and get some answers, so 0 by 1 is 0, plus 1 by 3 is 3. 0 by 2 is 0, plus 1 by 4 is 4. 2 by 1 is 2, plus 3 by 3, which is 9. That's 2 plus 9 is 11. And 2 by 2 is 4, plus 3 by 4 is 12. That gives us 16. So we get BA is equal to 3, 4, 11, 16. Now, it's really clear to see here that actually AB is not the same as BA. Matrix multiplication is not commutative. So there is a slight exception to that rule with commutative, and it's one we tend to meet when we're working in applied maths. So that is when we're talking about squaring a matrix, so multiplying it by itself. Obviously, if we multiply something by itself, they're both the same matrix, so if you flip the order, it's not going to matter. So bear that in mind when we're working with multiplication by itself. So the reason for this is because we're not really changing the order. We are, but we're not. It's like 3 by 3 and 3 by 3. We don't even know the order has flipped there. So just bear that in mind when we're working with squaring. Getting power 2 and even higher powers is something that is important for us in applied maths because it means something. And we're going to work later in the video to understand, well, what does that higher power, what does power on matrices really mean for us? But first, let's look at an example of squaring a matrix. So example 3, we're given the matrix A below and we're asked to find A squared. So we're asking to multiply A by itself. So we set this up exactly as we've set up our other ones. The only difference is both matrices are the same. So we have 1, 2, 3, 4 by 1, 2, 3, 4. So again, we're working always with row 1 first, then column 1. That gives us our answer for row 1, column 1 in our answer matrix. So we get 1 by 1 plus 2 by 3. And then we look at row 1, column 2, which gives us 1 by 2 plus 2 by 4. And then we look at row 2, column 1, 3 by 1 plus 4 by 3. And finally, row 2, column 2, which is 3 by 2 plus 4 by 4. Working each of those out, 1 by 1 is 1 plus 2 by 3 is 6. That gives the final answer of 7. 1 by 2 is 2 plus 2 by 4 is 8. That gives us an answer of 10. 3 by 1 is 3 plus 4 by 3 is 12. That gives us an answer of 15. And 3 by 2 is 6 plus 4 by 4 is 16. That gives us our answer of 22. So if we want to get A squared, effectively what we're doing is we're getting A, so A squared, and we get 7, 10, 15, 22. There's no magic shortcut for this. You're just going to work through like normal matrix multiplication. So let's talk a little bit about where these matrices appear when we're working in applied maths. So we're going to use square matrices to represent networks of connections. So we're going to work with something called an adjacency matrix where each row and column represents a node or vertex. So that could be a town, a person, or a computer. And if two nodes or vertices are directly connected, so we think of this as them being adjacent, so beside each other, we write the number of arcs or edges between them in the in the matrix. And then if they are not connected, if they've no connections, we write 0. So we're really getting how many direct connections. And we do mean direct, straight between each other, adjacent. So I'm not going to go any deeper into the idea of networks. If you want to go back and do a little bit of work on your networks, the video is linked in the description below. The focus of this video is just on matrices. So we will be linking to our networks, but I won't be going into any background about them. So this is example 4, and we're asked to find the adjacency matrix for the network below. Remember that adjacency matrix is just asking us to make a matrix storing the information about how many connections each node has. So to make this easier, I'm going to set this up with a little grid. You don't need a grid, but when you're working in your exam, you'll have square paper. If you're working in class, square paper can be helpful here just to see where everything goes. So our first space here, so let me get my zapper. So my first space here is where we put in the number of connections between A and A. So if we look at A, it doesn't directly connect to itself. Now you might say, well, how would it directly connect to itself? So again, if you want to go back, the video on networks is linked in the description below. But effectively what we will be looking for here is a loop. And there is no loop, so there is no connection. So we're going to put a 0 in there. So the next thing I'm going to look at, I'm going to go down, I'm going to look here in this space, which is how many connections between B and A. So that is B and A. I can see there's one there, so I put in my 1. But actually, this piece here is also representing how many connections between B and A. Well, really here it's A and B, but we'll talk more about the order when it begins to matter. So here I'm asking about A and B. So actually this is going to have a 1 as well. So then I'm going to fill in this piece here, which is how many connections between B and B. If we look at B, there's no loops, so that's just going to be a 0. Next, I'm going to fill in here. So how many connections between C and A? So I can see that there's one connection here. So I'm going to put in a 1. Again, here, I'm going to also look at the connections between A and C. So again, I'm going to put my 1 here. We'll talk a little bit more about that mirroring in a second. So then I fill in here. So C to B. So if I look C to B, there's actually no direct connection. So we get a 0 in here. There's also going to put a 0 here because there's no way to get from B to C directly either. Here I'm looking C to C. There's no loop, so I put in my 0. Next, I fill in here, so my D to A. So I have a connection between D and A, so I'll put a 1 in there. I also have the same connection between A and D, so I'll put my 1 in here. I'm here looking between D and B. There's actually no direct connections. That's a 0. I can also fill my 0 in here because there's no connections between B and D. Next, I look here, which is D to C. I have one direct connection, so I put my 1 in here. And I can also fill it in here, which is the connection between C and D. So that is my 1 goes here. And then for this corner, I'm looking at D to D. D has no loops, so this just is a 0. So let's fill in our last row and column. So then I have E to A. So there's actually no link between E and A, so that's a 0. Equally, there's no link between A and E. There is nothing there. So then I fill in here, which is E to B. So I can see I have my one side here. Equally, I have the one side between B and E. So that's my one side here. And I fill in my 1. Next, I look here, which is E to C. And if we look at the graph, E to C are not directly connected, so that's a 0. I also fill that in here, which is C to E. Next, I look at here, which is E to D. So E to D has one connection. And equally, there is a connection between D to E, which is also 1. And then lastly, in this corner is how many connections between E and itself. And the answer is 0. So that is our adjacency matrix for that particular network. So when we talk about adjacency matrix, we want to understand the type of graph we're working with. So what you need to understand here is that this matrix is actually symmetrical. So if I draw that red line through all those zeros, and I'll talk about why in a second, but we can see that it's symmetrical. And what I mean by that is there's a 1 here and a 1 here. 1, 0, 0, 1. 1, 0, 1, 1, 0, 1. 0, 1, 0, 1, 1, 0, 1, 0. Sometimes it can be hard to see that symmetry, but basically if you fold it, they would match. So this graph is called an undirected graph because it has no arrows. That means that each of these edges or arcs can go both ways. So I can go from E to B and equally back B to E. So think of it like a two-way street. Not all graphs will have these undirected edges. Some will end up with arrows. And if they have arrows, we have to take into account that things can only go one direction. So when I have an undirected graph, I'll always have a symmetrical matrix. So it's one way we can identify having an undirected graph. We can look at this lovely symmetrical matrix. And basically what's happening is the number of connections between A and D is the same as between D and A. So the edges really can go both ways. So example 5, so find the adjacency matrix for the directed network below. So we have a directed graph here. We know it's directed because of all these arrows. We have to follow the arrows, so we can't go against the arrows. So for example, A can go to B, but B has no direct route back to A. Now that's going to change how we fill in our matrix. And it's really important then to understand how we correctly read these paths. So we always read our matrices from left to top. What that means is, let me pick one here. So this box here is how many how many connections from C to B. So I go from the left to the top. So I read this way. So we're going to fill this in a little bit different because we're not going to have that symmetry. They won't necessarily mirror. So just if I find A to B, it's not going to be necessarily the same number from B to A. So let's fill in our first piece here. That's A to A. So there's no loop here at A, which means I have a 0. Next, I fill in A to B. Now, if we look, I have one direct link from A to B, so I can fill in my 1. Next, I go A to C, and again, I have one direct link here from A to C, and A to D. Now, there is an edge between them, but it's not going the right way. I can only go D to A. It won't let me back. So that means there's actually no way to go from A to D. It's really important you understand your order here. So there's no way to go from A to D. And finally, A to E. A and E are not connected at all, so there's no paths. Next, we focus on B. So we're going to look first B to A. Now again, although there's an edge between them, it's only going from A to B, it won't let you back. So there's no path. Sorry, well, there's no edge or connection between B to A. Then we have B to B, that is also 0. B to C, not connected at all, so also 0. B to D has that one connection, and B to E also has a one connection. Next, we look at C. C to A has no connection. Again, although there is an edge between them, C cannot travel to A, only A can travel to C. And then C to B has no connection at all. C to C has no connection. C to D has a single connection going that way. That's perfect. And then C to E has no connection. So next we look at D. So D to A has a connection. D to B, again, although there's an edge between them, it's not going the right way. So D to B is 0. D to C is also 0 because we don't have the arrow going the right way. And then D to D, now we can start to see, okay, so this is what I mean by a loop. We have D looping back to itself. So there's one way or one connection from D to D. And then here we have D to E, so we get our one connection. Our last row here is then E to A. There are no connections. E to B. Oh, again, although there is an edge between them, it's not going the right way. That's also 0. E to C. E to C are not connected at all. E to D are connected, but the arrow is the wrong way. You can't go from E to D, so that is 0. And then finally, E to E, there is no loop. So we get a 0. So this is really important to know it's not symmetrical. So if we pick something like here, this is B to A. There is no way to get from B to A, but there is a way to get from A to B. So we're not seeing that symmetry that we had before. So this is a nice idea. When you see a matrix, you're able to tell very, very quickly if we're dealing with a directed or an undirected graph, depending on whether it's symmetrical or not. Symmetrical basically will mean that we don't care. So symmetrical means we don't care about direction, or rather, every edge can go all directions. So here we can see that direction because of the arrows. That's what we're looking for. And it's just really important to note that A to B is not the same as B to A. Again, bear in mind you're always reading your matrices from the left to the top. So now let's look at the 2023 Ordinary Level Sample Paper, Question 7, Part A. Write the adjacency matrix that represents the graph shown below. So this graph has 4 nodes, so we're going to start off with our adjacency matrix with our 4 nodes down the side and across the top. So here we have an undirected graph. That means we're going to end up with a symmetrical matrix. When we're filling that in, we can do it a little bit quicker because of that symmetry. So let's start with our first piece here. That's A to A. A has no loops, so that's 0. Next, I'm going to fill in here. This is B to A. There is one way to get from B to A. And because it is undirected, there is the same number of ways to go A to B. So I have here a 1 again. Then I look from B to B. B actually has a loop, which means this is also going to be 1. Next, I fill in here, this is C to A. There's no direct link between C and A, so that is 0. Then we have C to B, which is, then we'll fill in A to C as well, which is also 0. Then we look C to B, which has a link, and we can do B to C at the same time, which has also got that one link or connection. Then we look at C to C. There's no loop here, so that is just a 0. Then we fill in D to A. There's no connection here. D to B has 1. And then we have, so D to B is 1, and we can equally fill in our B to D. That is also 1. Then here we have D to C. Now D to C actually has 2 edges or 2 arcs going to it. So we fill in our 2. And then we can fill that in here as well, because this is C to D. So D to C goes twice, but C to D also has twice coming back. And then finally we have D to D, but there's no loops. So that gives us our 0. So this is the 2023 Ordinary Level Sample Paper, question 7, part B. The matrix P2101 and the matrix Q30 minus 22 calculate PQ. So let's set that up. We have these two to multiply together. We focus first on our first row of the first matrix by the first column of the second matrix. That gives us 2 by 3 plus 1 by minus 2. Next, we look at row 1 by column 2. That's 2 by 0 plus 1 by 2. Next, we look at row 2 by column 1. That is 0 by 3 plus 1 by minus 2. And finally, we look at row 2, column 2, which is 0 by 0 plus 1 by 2. Working those out, 2 by 3 is 6, plus 1 by minus 2 is minus 2. 6 and minus 2, we get a 4. Then we get 2 by 0 is 0, plus 1 by 2 is 2. That gives an answer of 2. 0 by 3 plus 1 by minus 2. That gives us a 0 minus 2, which just gives us a minus 2. And 0 by 0 plus 1 by 2 just gives us our answer of 2. Our final answer for PQ then is 4, 2, minus 2, 2. This is question 1, part AI from 2023 Ordinary Level Paper. The diagram below shows a graph with 5 nodes, A, B, C, D, and E. Write the adjacency matrix for this graph. So the first thing you want to do is to give yourself the space to have the 5 nodes both in the rows and the columns. So we're looking at a 5 by 5 matrix. And the adjacency matrix, remember, just tells us how many connections appear between each of the nodes. Because this graph is undirected, we're going to end up with a symmetrical adjacency matrix. This means we don't have to worry too much about the order that we're moving. So our first piece here is A to A, and there are no connections between A and A itself. So what we'd be looking for in that case will be a loop. I'm going to work down. So the next one I'm going to work with is B to A. So there is one connection between B and A, and that is the same between A and B. So I'm going to fill those both in as 1. Then we look at B to B, and there are no connections between B and B. The next one I'm going to look at is between C and A. There are no connections. This means there's also no connections between A and C. Then we look between C and B, and there is one connection, and this is mirrored as the same between B to C. So remember, the order doesn't matter, so we're seeing that mirroring effect. And then C to C, there are no connections. Then we look from D to A, and there is no connections between D to A, and then we can mirror that by looking at the connections between A and D, and there is none. Then D to B, there are no connections, which again we can mirror between B and D. And then D to C has one connection, which means there's also just one connection between C and D. And then between D and D, we have our loop, so we do have that one connection there. Then I'm going to work from E to A. There's actually two connections, which is mirrored in A to E, so we can put our 2 here as well. We then look E to B. There are no connections, so no connections between B and E as well. Then we look E to C. There are no connections, so equally no connections between C and E. E to D has one connection, which is mirrored in D to E. And then finally, E to E has no connections. So this is what our adjacency matrix looks like for that graph. So question 1A part 2 from the 2023 ordinary level paper. Matrix A is given as 3, 4, minus 1, minus 2, and matrix B is given as minus 1, 2, 0, and 3. And we're asked to calculate AB. So we're being asked to multiply these two pieces together. So when we're working with any kind of matrices, we're first of all working with the row of the first matrix by the column of the second matrix. So our first entry is row 1, column 1, which is going to be 3 by minus 1 plus 4 times 0. Then we work with row 1, column 2, which is going to be 3 times 2 plus 4 times 3. Then we work with row 2, column 1. Remember, it's all based on the position in our final or resultant matrix. That is minus 1 by minus 1 plus minus 2 by 0. And then finally, we have row 2 by column 2, which is going to give us minus 1 by 2 plus minus 2 by 3. When we do these calculations out in full, we get a minus 3. We get 18, so 3 by 2 is 6, plus 4 by 3 is 12. And then for row 2, column 1, minus 1 by minus 1 is plus 1, plus is 0, so that gives us just 1. And then in our final entry, we get minus 2 plus a negative 6, which gives us a minus 8. Our final answer for AB is minus 3, 18, 1, minus 8. So let's take a look at question 1 part A from the 2024 higher level paper. Matrix A is given as this and matrix B is given as that. So they're both 3 by 3 matrices and we're being asked to calculate A by B. So here we have our two matrices. It's really important to put A first, then followed by B. Remember that when we're multiplying matrices, they are not commutative. Matrix multiplication is not commutative. The order really does matter. We're going to start with row 1 in the first matrix multiplied by column 1. That gives us minus 1 by 5, 0 by 0, 2 by 2, which gives us a value of minus 1. Then we move to column 2. That gives us minus 1 by minus 1, 0 by 4, and 2 by minus 1, and a final answer of minus 1. Then we have row 1 by column 3. That's minus 1 by minus 2, plus 0 by 3, plus 2 times 0. And that gives us a final answer of 2. Then we move to row 2 and multiply that by column 1. So we get 3 by 5 plus 1 by 0 plus minus 1 by 2 gives us 13. Then we have row 2 by column 2, 3 by minus 1, 1 by 4, minus 1 by minus 1, final answer of 2. Row 2 by column 3, 3 by minus 2, 1 by 3, and minus 1 by 0 gives us an answer of minus 3. Then we look at row 3, column 1. That is 0 by 5, 2 by 0, and minus 3 by 2. That gives us final answer of minus 6. Row 3, column 2. That gives us 0 by minus 1, 2 by 4, and minus 3 by minus 1, which equals 11. And then row 3 by column 3, and that gives us 0 by minus 2, 2 by 3, and minus 3 by 0, and the final answer equal to 6. And that gives us AB is equal to minus 1, minus 1, 2, 13, 2 minus 3, and minus 6, 11, and 6. So now let's take a look at question 1 part A from the 2023 deferred higher level paper. So we have two matrices here. They're both 3 by 3s. We have A and we have B, and we're asked to calculate A by B. So first thing we want to do is just set up our multiplication, and then our focus is going to be on the row of the first by the column of the second. So row 1 by column 1, and that's going to give us minus 1 by 0, 0 by 3, and 2 by 1, and gives us an answer of 2. Then we look at row 1, column 2, so that is minus 1 by 1, 0 by minus 2, and 2 by 4. That gives us 7. And then finally row 1 by column 3 to complete the first row of our answer, and that gives us minus 1 by 2, 0 by 0, and 2 by 0, which gives us minus 2. Then we move into row 2, so we work row 2 by column 1. That's 4 by 0 plus minus 3 by 3 plus 0 by 1, which gives us a final answer of minus 9. Then we have row 2 by column 2, that's 4 by 1 minus 3 by minus 2, and 0 by 4, which equals 10. Then we have row 2 by column 3, that gives us 4 by 2 plus minus 3 by 0 plus 0 by 0, which gives us a final answer of 8. And then on to our last row, so row 3 by column 1, that gives us 1 by 0 plus 2 by 3 plus 1 by 1, an answer of 7. Row 3 by column 2, 1 by 1, 2 by minus 2, and 1 by 4. That gives us an answer of 1. Final entry is going to be row 3, column 3, and that's 1 by 2, 2 by 0, and 1 by 0, which gives us an answer of 2. So final answer for AB is 2, 7, minus 2, minus 9, 10, 8, and 7, 1, 2. The second part of this question asks us to verify that AB does not equal BA. So we have our AB here. To get BA, we flip the order. Remember, matrix multiplication is not commutative. The order is important. So here we've flipped, so B comes first and then A, and we can work it through. So row 1 by column 1 gives me 0 by minus 1, 1 by 4, and 2 by 1. That gives me 6. That entry alone is enough to show that they can't be equal, because for AB, the first entry is 2. So this answer is 6. So straight away, you can stop here. You don't need to do the full multiplication. It is enough to show, well, if even one entry is different, they can't be identical. So we can stop there. Now, if you want to continue with your multiplication, and maybe just for practice more so than anything, in an exam situation, you wouldn't do this. So here is what it works out as if you want to do that full multiplication for BA. It's always good to get a bit of extra practice. And then our final answer for BA is 612 minus 1166. 15 minus 12, 2. And we can clearly see that they are not the same. They have one entry in common, and that's the one at the bottom right. So the last two, but other than that, they're all different. So let's talk about squaring adjacency matrices. So this is something we see a lot on the applied maths course, and not just squaring them, but what does it mean? So what are we getting? What information is it telling us when we square the adjacency matrix? So what we're doing is we're taking our adjacency matrix, let's call it A, and we're giving it a power 2. So what we're actually finding out is how many different walks or paths of length 2 exist between a pair of nodes. So when we talk about a walk or a path, it's a way of getting from one node to the other using multiple edges. So starting at one, ending at another. So what happens if we talk about higher powers? So if we talk about a to the power of 3, a cubed, we're talking about the number of walks of length 3. And a to the power of 4 be number of walks of length 4, and so on. So this can be something that be quite hard to do by hand, especially as the lengths get a little bit longer and the number of paths increase. It's easy to like forget one. But let's look at a number example that will help us understand this better. So this is the 2024 Ordinary Level Paper, Question 5, Part A, Part 2. Another adjacency matrix is given as n is equal to 0, 2, 3, 1. Calculate n squared and explain what the entries of n squared represent. So here are our two matrices. So they're both the same. We're multiplying it by itself. And to get our answer, we're going to work with row 1, column 1. That's going to give us 0 by 0 plus 2 by 3, which gives us our 6. Then we do row 1 by column 2. That's 0 by 2 plus 2 by 1. Row 2, column 1 gives me 3 by 0 plus 1 by 3. And then finally we have row 2, column 2, 3 by 2 plus 1 by 1. That gives us our 6, 2, 3, and 7. So that's our answer for n squared. But then it asks us to explain what the entries in the matrix n squared represent. So in order to truly understand this, what we're going to do is we're going to draw out the original graph that n represents. So this is it. There are two nodes. We have 0 connections between A and A. There are 2 connections between A and B. Because this is not symmetrical, I know it's a directed graph. So when I went A to B, I put an arrow on it and a second line with an arrow on it. But then there's 3 ways to get from B to A. So rather than having extra lines, I just said, well, of 2 of them, B can also go back, and then it has its own path. As well. So that's our 3. And then this last one is B to B, which is our lovely loop. So then if we take our n squared, we're looking at the number of walks of length 2. So if we take that 6, it's telling us that there's 6 walks of length 2 from A to A. So let's find them. Let's see them. So here's A, and I want to go 2 steps and get back to A. So first option is just go here and here. So that's 1. The next is go over, but come back this way. 2. The next is go over the same way, but come back this path. So that's 3. Then we could go over this way and back the same one. That's 4. Over the same way again, back here. That's 5. Over the same way again, but come back here, and that is 6. That is our 6 walks of length 2 from A to A. So going 2 steps and we're back to A. We then have this 2. So there's 2 walks of length 2 from A to B. So our options are we go over this path and we go around the loop. So that's 1. Or we come over this path and loop. So there are 2 options. Then when we have that 3, there are 3 walks of length 2 from B to A. So notice that the number of walks from A to B is not the same as B to A. So if we go B to A, we can go... Sorry, we have to do a loop first, and then we go here. So that's 1. Or loop and this path, that's 2. And then loop and this path, so that's our 3. And then there are 7 walks of length 2 from B to B, which I'm not going to show you all of them, but it is a nice exercise to see. Can you find them all? It's nice for us to have a mathematical way of figuring out how many of them exist, and we're not relying on simply counting them. This is question 1A from the SEC sample higher level paper. A directed graph is represented by the adjacency matrix M, which is 0, 0, 2, 1, 1, 0, 0, 1, 0. Draw the graph represented by M. So I'm going to label the nodes A, B, C, so that allows us to make sense of it. So I know that there's only 3 nodes because it's a 3 by 3 matrix. So there is A, B, C, and here is A, B, C. So my 3 nodes A, B, C are here. Let's look at each entry and see if we can make sense of it. A to A, there is no connection, so there's no loop. A to B, there are no connections. So then we're looking A to C, and it has two connections. So remember, this is a directed graph, which means we're going to show any lines with arrows. So this is A to C. We read left to top. So A to C has our two connections there, so we get rid of that. Then we look, B to A has one connection, so that's going to be a directed arrow from B to A. B to B has one connection, which gives us a loop at B. B to C has no connections. Then we have C to A, so there's no connections that way. Then we have C to B, so we have a directed arrow going this way. And then finally, C to C has no connections. So this is what the final graph represented by the matrix M looks like. So then it asks us to calculate M squared. So we're taking our matrix M and we're multiplying it by itself. So we're doing a 3 by 3. Our focus is on multiplying the rows in the first matrix by the columns in the second. So we start with row 1 and multiply it by column 1. That works out as 0 by 0 plus 0 by 1 plus 2 by 0, which gives us a final answer of just 0. Next, we do row 1, column 2. It is 0 by 0, 0 by 1, and 2 by 1, which gives us just an answer of 2. Then we do row 1 by column 3, 0 by 2, 0 by 0, and 2 by 0. That gives us a final answer of 0. Then we move to row 2, and we multiply that by column 1. So row 2, column 1 gives me 1 by 0, 1 by 1, and 0 by 0. Final answer is 1. Row 2 by column 2, it gives us 1 by 0 plus 1 by 1 plus 0 by 1. That gives a final answer of 1. And then row 2 by column 3, 1 by 2 plus 1 by 0 plus 0 by 0, which gives us our 2. And then we work with our final row, so row 3 in the first matrix multiplied by column 1. That's going to give me 0 by 0, 1 by 1, and 0 by 0, which gives us an answer of 1. At row 3 by column 2, that's going to give us 0 by 0, 1 by 1, and 0 by 1. That gives us a final answer of 1. And for the last entry, we're doing row 3 by column 3, and that gives us 0 by 2 plus 1 by 0 plus 0 by 0, which gives us a final answer of 0. So our final answer for M squared is 0, 2, 0, 1, 1, 2, and 1, 1, 0. So in the final part of this question, what information is provided by the elements of M squared? So this is our M squared that we've just worked out, and what we're trying to explain is, what does each number represent? And because it's m to the power of 2, we're talking about walks of length 2. So each number in this matrix gives us the number of walks of length 2 between two nodes. And it can even be between the same node, so A to A. So a really good way to explain this clearly in an exam is to take an example. So here we take the 2. So if we label this ABC, ABC, here we're talking about the number of walks of length 2 between, well, going from A to B, and that's really important. So there are 2 walks of length 2 from A to B. Really keep an eye on your order there.